Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're here today because we are going to unpack one of the most fascinating intellectual journeys of the entire 20th century. We're going to explore how scientists from completely different fields, I'm talking biology, engineering, mathematics, all essentially woke up and realized the exact same thing. And that is, studying isolated parts just doesn't give you the whole picture. So let's get right into the history and foundations of system science.
It's a great question, isn't it? And it really sets up this massive historical mystery. Think about it. For hundreds of years, traditional science was incredibly successful by just breaking things down. If you wanted to understand how something works, you take it apart. But eventually, science just hit a wall. Researchers started to realize that organisms, economies, ecosystems, and these massive technological grids, they possess properties that literally vanish the second you chop them up into individual pieces. The behavior of the whole is somehow born from the interactions themselves. So how do you even begin to study that?
Okay, let's dive into this core paradigm shift. First step, we've got reductionism. This is the old way of doing things, studying isolated components. It's kind of like trying to understand an entire forest by exclusively staring at individual leaves under a microscope. I mean, sure, you're going to learn a whole lot about leaves, but you'll learn absolutely nothing about the actual forest ecosystem. But then you have system science. This is the practice of studying organized wholes and the relationships. It's zooming way out to see the big picture, the entire forest, and understanding how the trees interact with the soil, the animals, and the weather. So how did we actually get to this zoomed out perspective? Well, system science wasn't just invented by one person having a eureka moment in a single lab. It was a massive convergence, basically a merging of different intellectual rivers over time. The journey really kicks off in the early 1900s with Bogdanov, flows through the post-war era with Wiener and Boulding, surges into the computer age with Forrester, and finally reaches the complex thermodynamics of Prigogine in the late 70s. Biology, engineering, and math all gradually converged to form what we know today as modern system science. Let's trace these streams, shall we?
Stream 1, beyond the isolated parts. This is where biology begins to map out universal organization.
Our first pioneer here is Alexander Bogdanov in the early 20th century. And let me tell you, Bogdanov was incredibly ahead of his time. He created this framework he called techtology. His bold, almost sci-fi idea at the time was to find universal organizational principles that applied equally across biological, social, and technological systems. Unfortunately, his work remained largely unknown in the Western scientific community for decades. But looking back now, we can see he brilliantly anticipated the modern systems theory that was just about to explode onto the scene. And that explosion really happened with Ludwig von Bertalanffy's general systems theory. He gave us this absolutely crucial definition of open systems, systems that exchange matter, energy, and information with their environments. Now, before this, the traditional mechanistic view of science often treated systems as closed and static, kind of like a sealed clockwork machine. Bertalanffy completely shattered that idea. A living organism isn't a closed clock. It's open. It's constantly breathing, eating, and reacting to its environment. And he argued this transdisciplinary framework could reveal patterns across biology, society, and technology alike.
Building on that momentum, in 1956, Kenneth Boulding gave us a way to visualize how this complexity scales up. He classified systems hierarchically. So, step 1 at the base, you've got simple physical structures. Step 2, moving up the ladder, we get biological entities, which add life and dynamic equilibrium into the mix. And finally, step 3, right at the top, complex social systems, introducing human interaction and culture. He beautifully showed how organizational complexity naturally just scales up the ladder of reality.
Okay, so we understand that systems scale up and that they're totally open to their environments. But that brings us to a really fascinating pivot. If a system is open and constantly bombarded by its environment, how do these systems actually regulate themselves? I mean, how does an organism stay alive or a machine stay on course without just spinning out of control? Well, that brings us to Stream 2, cybernetics and control. Here, we're stepping right into the realm of engineering, animals, and machines. Now, what's really interesting here is the introduction of the ultimate survival tool, feedback. In 1948, Norbert Wiener developed cybernetics, officially introducing the concept of feedback processes. This is the mechanism that allows a system, whether we're talking about a living animal or an artificial machine, to monitor its own state and adjust its behavior in response to environmental changes. Think of a thermostat checking the room temperature to decide whether to turn the heat on or off. That simple, everyday feedback loop, that is the very foundation of self-regulation.
Then, W. Ross Ashby took this a step further with the principle of requisite variety. Let me translate this academic concept for you because it's actually incredibly profound. Simply put, it means that your coping mechanisms must be at least as diverse as the stress or complexity you're facing. If the environment throws 10 different types of disturbances at a system, that system needs at least 10 distinct types of responses just to maintain stability. If the environment is more complex than your regulatory capacity, the system breaks down. It's that simple. But wait, we didn't just leave these concepts to the engineers. Stafford Beer took these ideas about machine and animal regulation and beautifully applied them to human organizations. A real game changer. He created management cybernetics and the viable system model. He realized that businesses, governments, institutions, they're all just systems trying to survive in complex, changing environments too. By applying cybernetic feedback loops to governance, he showed us exactly how organizations can adapt and remain viable. But, of course, as systems get bigger, they get way harder to track. So let's move to Stream 3, System Dynamics and Math.
By 1961, Jay Forrester hit the scene with system dynamics. Look, when you have multiple feedback loops, time delays, and nonlinear interactions all happening at the exact same time, human intuition just fails. We literally cannot track it all in our heads. Forrester's genius was using mathematical models and early computer simulations to visualize these wild dynamic patterns. He mapped out how these interactions generate massive cycles of growth, sudden decline, or oscillation. He showed us that to truly wrap our heads around complex systems like a city or an economy, we absolutely have to simulate them mathematically.
And Anatole Rappaport was the crucial translator in all of this. He provided the formal mathematical frameworks needed to take these super abstract theoretical concepts and apply them directly to studying real human behavior and social sciences. He essentially gave researchers the mathematical language to take these big ideas about systems and actually put them to work in real-world policy and human behavior.
Which brings us to our final historical stream, Stream 4, the rise of complexity. We are taking this to the very edge of chaos. And this brilliantly illustrates one of the most magical concepts in modern science, self-organization. Complexity science looks at how massive numbers of interacting components generate entirely new emergent behaviors. Self-organization is how patterns and structures emerge spontaneously from local interactions without any centralized control whatsoever. Think about it. There is no CEO bird telling a flock how to fly in perfect formation, right? The order just emerges entirely on its own, from the bottom up. In 1977, researchers like Nicholas and Prigogine proved this mathematically and thermodynamically. They demonstrated that when systems are pushed far from equilibrium, when they are highly energized, completely chaotic, they don't just fall apart. Actually, through nonlinear interactions, they can spontaneously develop highly structured patterns. They proved for sure that chaos and instability can actually be the birthplace of incredible order and entirely new structures. The convergence, an integrative field. Let's bring all of these historical streams together now. So biology, engineering, math, and physics, they all finally merged into the integrative field of system science that we rely on today. And today, this field has massive, real-world utility across the board. In ecology and the environment, system science is the absolute foundation for studying resilience and sustainability. In computer science and physics, we use it to map complex networks, like the internet or even neural pathways in the brain. And in economics and society, it allows us to model adaptive socio-ecological systems. System science isn't just some abstract theory anymore. It's basically the operating system for modern problem solving. Ultimately, all of this rich history boils down to a single core mission. Despite the huge diversity of approaches we've talked about, from Bogdanov's techtology way back when to Prigogine's thermodynamics, the central goal remains consistent: to understand how systems organize, interact, adapt, and evolve across different domains of reality. That is the core mission. It's the grand search for the universal rules of the game. As we wrap up, I want to leave you with this really provocative thought to chew on. We live in an era where our global economy, our artificial intelligence networks, and our super fragile ecological systems are deeply, deeply intertwined and constantly colliding. We have created a world of truly unprecedented complexity. So the big question is, using the foundations of system science, are we actually equipped to govern the complexity we've created? It's something we all need to be thinking about. Thanks so much for joining me on this explainer, and remember to always keep looking at the big picture.